Okay, so it's my turn. So good afternoon, everybody. My name is François Légaré. At least in Montreal, it's very nice day today. Finally, we see summer. I don't know if it's the case for all of you, but thanks to be here instead of going outside and taking light from the sun. So instead, we will hear about what we can do today with intense light, with plasma. So the seminar today is shiny and brilliant laser plasma interactions for everyone. The presentation will be given by Mangaljit. Mangaljit did his PhD with Professor Tsuneyuki Ozaki at INRS. And he was very productive during his PhD, making very good publications. After PhD was for a short period of time postdoc, and then he has recently joined the Advanced Laser Light Source Facility as a research associate. So today he's going to discuss the work that he has performed with Professor Ozaki. So it's your time, Mangaljit. Thanks to be with us.
Thank you very much. Can you see my screen? Everything is fine?
Yes, perfect.
Okay. Okay, thank you very much, François, for the kind introduction. The title of my talk for today is Studies on Resonant High-Order Harmonic Generation from Laser-Ablated Plumes, Some New Perspectives. My name is Mangaljit Singh. As François mentioned, I'm a research associate at ALS, INRS. These are the contents of my today's presentation. I'll start by introducing the concept of high-order harmonic generation, which will be followed by the explanation of the generation mechanism using three-step model. Then I will introduce the concept of resonant high-order harmonic generation, and then what different kinds of resonances can influence the harmonic generation process. And this will be followed by the explanation of the mechanism using four-step model. And then I'll discuss briefly the experimental setup and some of the recent experimental results that we observed in our experiments. High-order harmonic generation process is an extremely nonlinear optical phenomenon that takes place when an intense femtosecond pulse, typically of visible or infrared wavelength, interacts with an interaction region. And this results into the generation of extreme ultraviolet and or soft X-ray radiation, the coherent pulses. So HHG, the high-order harmonic generation process, provides an excellent tabletop source of coherent XUV and soft X-ray radiation. And if we perform the HHG with sufficiently short femtosecond pulses, then this process has the potential to generate coherent XUV pulses of attosecond time duration. Now, talking about the interaction region, this region can contain gases, it can contain bulk crystals, it can contain solid surfaces, or as is our case, laser-ablated plume. So we are basically interested in studying the HHG from laser-ablated plumes. All the experiments that we perform were performed at Advanced Laser Light Source Laboratory, which is located at INRS EMT in Quebec, Canada. This is the quick overview of the laser source that we use for our experiments. So in ALS, we have amplified titanium sapphire laser source at 100 Hertz repetition rate, which can provide up to 80 millijoules of compressed femtosecond pulses. We can use this laser directly if we need 800 nanometer, or we can drive the optical parametric amplifier source using this laser. And this optical parametric amplifier can provide us tunable laser pulses of wavelength around 1.8 micron. And further, the output of the optical parametric amplifier is amplified using a BBO crystal. And we can have about 10 to 11 millijoule of pulse energies at 1.8 micron with about 35 femtosecond pulse duration. And if we need to further compress the pulse duration, we have the hollow core fiber pulse compression system. And with this, we can obtain about 12 femtosecond pulse durations at 1.8 micron, which is about 2 cycles, and with an approximate energy of 4 to 5 millijoules. This is the schematic diagram for the experimental setup for generating harmonics from laser-ablated plume. We have a solid target, and from one direction, we focus a laser pulse, which we call as pre-pulse. And this intense pulse, when focused on the solid surface, will generate the laser-ablated plume. And then from the orthogonal side, we focus another laser pulse near to the plasma, near to the laser-ablated plume, and we get the generation of high-order harmonics collinearly with the incident driving laser. And then to separate the driving laser from the XUV, from the harmonics, we have installed a silicon mirror at the Brewster angle, which will only reflect the XUV. And then to see the spectrum of the XUV, we spectrally disperse the XUV using a grating. And finally, the generated spectrum is recorded with the combination of MCP and phosphor screen. To do the ablation of the solid target, we use stretched picosecond laser pulses with the typical pulse energies of half to 1 millijoule at 800 nanometer. And then for the main pulse, which is used to generate harmonics, is a compressed pulse with about 50 femtosecond pulse duration. And the driving laser wavelength for the main pulse could be visible, it could be near infrared, or it could be mid infrared. It depends on what kind of phenomenon we want to observe in the laser-ablated plume. And the typical pulse energy is between 2 to 10 millijoules. And here is the typical high-order harmonic spectrum that we observe from, for example, here a graphite laser-ablated plume, which is driven with a 17, 18 nanometer laser. And in this case, we have about the cutoff, which is the maximum harmonic order. In this case, at the given laser conditions, is about 89th harmonic order. So there are several advantages of studying or generating harmonics from laser-ablated plume as compared to other methods. For example, if we compare it with the solid surfaces, then these kind of methods require laser intensities of the order of 10 power 18 watt per centimeter square. However, in our case, we can use laser intensities of the order of 10 power 14 watt per centimeter square. And then talking about the generated XUV flux from the laser-ablated plume method, then as I will explain in the coming slides, that the presence of different kinds of resonances can influence the generation process, the harmonic generation process from the laser-ablated plume. And these resonances can enhance the conversion efficiency for the generated XUV, and we can have very high of the order of 10 power minus 4 conversion efficiencies in the presence of resonances. And this efficiency is about 2 orders of magnitude higher than the typical conversion efficiency obtained from gases. And then thirdly, because we can use any solid target to create the plume, then that's why we have a large number of solid elements that are available to study the harmonic generation process. On the other hand, if we talk about gases, then we have very few gases which can be exploited to study the harmonic generation process, the HHG. Here is the mechanism of the harmonic generation process, which is called the 3-step model. So when we shoot the ultrafast laser pulses on the interacting media, then in the first step, an atom or ion, when it interacts with the ultrashort laser pulse, in the first step, the valence shell electron gets tunnel ionized under the influence of the incident electric field of the ultrashort laser pulse. After the tunnel ionization, in the second step, the tunnel ionized electron gets accelerated towards the continuum under the effect of the laser pulse electric field. And finally, in the third step, when the laser pulse electric field reverses the direction, the tunnel ionized electron comes back to the initial ground state, it gets recombined, and this recombination results into the generation of higher order harmonic generation process. And the maximum photon energy that can be generated from the higher order harmonic generation process is the sum of the ionization threshold of the atom or ion, which is participating in the harmonic generation process, and the maximum kinetic energy of the electron that is returning back to the initial ground state. So the cutoff is the sum of the ionization potential and the maximum kinetic energy of the electron. And the cutoff energy scales as linearly as the incident intensity of the driving laser, and scales as the square of the wavelength of the driving laser pulse. So to increase the cutoff, we can increase the driving laser wavelength or the intensity of the incident laser pulse. Here I have shown the two interesting harmonic spectra, one from the indium and other from the tin. So if we compare, if you look at the spectrum of graphite, we can see that the harmonic intensity of the individual harmonics are comparable to their neighboring harmonics. And then it varies in a very smooth manner, it goes to the cutoff. But in case of indium and tin, we can see that one particular harmonic order has intensity which is much higher than the other neighboring harmonics. And similar is the case with the tin. So in indium, we have the 13th harmonic resonant, 13th harmonic order, which is enhanced at 800 nanometer. And in case of tin, we have the 17th harmonic order, which is enhanced at the 800 nanometer laser. And when we look carefully, we find there are two electronic transitions. There are electronic transitions present in both indium and tin, which correspond to the energy of the enhanced resonant harmonic. For example, in case of indium singly charged ion, there is an electronic transition with a very high oscillator strength that corresponds to about 19.92 eV, which is 13 photon resonant with the 800 nanometer. And this is why we have intense 13 harmonic resonant, enhanced 13 harmonic resonant. And similarly, in case of tin, we have the electronic transition at 26.3 electron volt, which is a 17 photon resonant with the 800 nanometer laser. And we have the corresponding 17th harmonic order enhanced in terms of intensity when compared with the neighboring harmonics. And these kind of resonant harmonics have shown to exhibit a very high 10⁻⁴ level conversion efficiency. So for example, if you use 10 millijoule of laser pulse energy, we can generate a microjoule level XUV pulse energy from these kind of resonances. And as I said earlier, this is about 2 orders of magnitude higher than the typical conversion efficiencies observed from the noble gases. So talking about the mechanism of harmonic enhancement, so the presence of these strong electronic transitions in the continuum correspond to the location of an auto-ionizing state above the ionization threshold in the continuum. So to explain the harmonic enhancement mechanism, the 3-step model gets modified into the 4-step model. So the first 2 steps remain the same. That is the tunnel ionization of the valence shell electron, and then its acceleration towards the continuum. However, in the 3rd step, instead of directly recombining in the ground state, the tunnel ionized electron gets trapped in the auto-ionizing state. It's captured by the auto-ionizing state, and finally, in the 4th step, it again gets recombined into the ground state, emitting the intense resonant harmonic. Apart from auto-ionizing state, there are different other kinds of resonances that can influence the harmonic generation process. For example, we can have resonances from the inner shells, which we call inner shell resonances. We can have resonances from the various Rydberg states, which are located just below the ionization threshold. Or we can have resonances from the dressed auto-ionizing states. these are the states, these are the laser-driven virtual states. So we can have resonances from these kind of dressed auto-ionizing states as well. So starting with the first part of the experimental investigations that I will discuss today, I'll talk about the generation of harmonic, high-order harmonic in the multiphoton ionization regime. So previously we talked about the three-step model, which involved the tunnel ionization, which is the ionization of the electron due to the bending of the Coulomb potential under the influence of laser electric field. However, apart from tunnel ionization, there could also be a multiphoton ionization where the valence electron can absorb multiple incident laser photons to make the transition, to undergo the ionization. And very important parameter, which is called a Keldysh parameter, can give us an idea that under given laser conditions, which one of these two mechanisms dominates. And this Keldysh parameters is essentially a ratio of ionization threshold and the ponderomotive energy, which is the cycle average kinetic energy of the electron. So for laser conditions, if the Keldysh parameter is less than 1, then the tunnel ionization dominates. And if the Keldysh parameter is greater than 1 under the given laser conditions, we can have multiphoton ionization mechanism. And if we look carefully at the Keldysh parameter, we can see that it is essentially a ratio of IP and UP. So under given laser conditions, if the ponderomotive energy, which is essentially the kinetic energy of the tunnel ionized electron, if this is much lesser than the ionization threshold, then we can see that this creates a good conditions for the multiphoton ionization to dominate, because the kinetic energy is not sufficient enough to overcome the ionization threshold, and vice versa for the other condition, for the gamma less than 1. So these two mechanisms can influence the ionization process under given laser conditions. And the spectrum that I showed you previously from the graphite laser-ablated plume, this was recorded at the laser conditions which correspond to the tunnel ionization mechanism. That is, the Keldysh parameter is less than 1. And as I explained earlier, in the tunnel ionization mechanism process, the harmonic generation spectra is very broadband, which contains multiple harmonic orders, which are odd multiples of the incident laser driving photon energy. However, there are many applications which require quasi-monochromatic XUV light. So instead of very broadband spectrum, some applications require quasi-monochromatic XUV light. Some of the examples are angle-resolved photoemission spectroscopy, photoemission electron microscopy, XUV diffraction imaging, or XUV lithography. So in these kind of applications, we have to employ special XUV monochromators, which are based on the gratings. So we have to filter out one given harmonic order of interest for the experiments. However, because these gratings have a very limited diffraction efficiency, so these kind of setups typically result into a flux loss for the XUV, which is typically greater than 70%. And to overcome this problem, we decided to investigate the harmonic generation process in the multiphoton ionization regime. So for these studies, we chose gallium as the target for generating the plume. In gallium, we have an auto-ionizing state that corresponds to about 21.9 electron volt energy. And this is 15 photon resonant with the 860 nanometer laser and 7 photon resonant with the 400 nanometer laser wavelength. These are some of the harmonic spectra that we generated from different near-infrared laser wavelengths. So as I said, there is a resonance at 21.9 electron volts in case of gallium ions, which is 15 photon resonant with the 860 nanometer laser, and we have the resonant intensity enhancement of the 15 harmonic order compared to the other neighboring harmonics. And as we shift the laser wavelength away from the resonance, we can see that the intensity of the harmonic order diminishes, which clearly indicates the effect of resonance with the driving laser wavelength. And to estimate the enhancement order of the resonant harmonic, we have used this equation, which essentially compares the intensity of the resonant harmonic order compared to the neighboring harmonics. So at the given laser conditions at 860 nanometer laser wavelength, we have an enhancement ratio of 136. And the gamma parameter, which is the Kildish parameter, is about 0.935. And then after these experiments, we decided to further lower down the driving laser wavelength. So we use the 400 nanometer laser wavelength for these studies. And at 400 nanometer laser wavelength, the gallium resonance is 7-photon resonant. And again, we observed a very high intensity enhancement of the 7th harmonic when compared to the neighboring harmonics. And in this case, at 400 nanometer laser, the Kildish parameter is 2. And that means that the multiphoton ionization process dominates. And as we can see, the ponderative energy is much lesser than the ionization threshold. And the multiphoton ionization process dominates. And at 400 nanometer laser, the enhancement ratio observed is about 714. And this is the maximum enhancement ratio that has ever been reported using the plasma plume method. And if we compare the intensity of the resonant harmonic order at 400 nanometer with the 860 nanometer laser, so we have about an enhancement of about 4.5 times. And to understand the reason that why the enhancement ratio increases when we increase the Kildish parameter, or why the enhancement ratio increases when instead of having the ionization by the tunnel ionization, we have the ionization by the multiphoton ionization. So we looked at the wave function of the electron at two different conditions, one for the multiphoton ionization condition and other for the tunnel ionization condition. And these calculations were performed by our collaborator, Professor Vasily Strelkov. And one distinct difference that we see is that the wave function is has much more spread in the tunnel ionization regime as compared to the multiphoton ionization regime. And this makes sense because in case of tunnel ionization regime, the electron has to tunnel ionize, it has to propagate in the continuum and then come back to the ground state. Because of this propagation effect, there is a diffusion of the electron wave function. And when it again recombines to the ground state, this diffusion of the wave function results into a reduced overlap with the ground state, which results into the reduced enhancement ratio for the resonant harmonic. So as I said earlier, at 860 nanometer, we have about 136, the enhancement ratio. And at 400 nanometer, we have 714. And our the calculations qualitatively reproduce the results that when we reduce the laser wavelength or when we increase the Kildish parameter, the enhancement ratio gets increased. And then we compare the intensity of the resonant harmonic from gallium with some of the previously known targets, which are known to generate intense harmonics. So for example, previously tin resonant harmonic, which is at 26.3 eV, is known to generate intense microjoule level resonant harmonic energy. And when we compare tin with the resonant harmonic of gallium, then this resonance is about 3 times higher than the tin. So that means we can easily generate about 3 to 4 microjoule of pulse energies at high 10 power minus level, -4 level conversion efficiency. So in these experiments, we did not measure the XUV flux of the resonant harmonic. We plan to do these experiments in the future, but the relative comparison with other targets show a very good promising shows a very good promise that the resonant harmonic of gallium can generate multi-microjoule XUV pulse energies. And the resonant harmonic of the gallium has a bandwidth of about 0.28 electron volts, which under Fourier transform limited conditions can provide about 6.5 femtosecond of pulse duration. So this is the conclusion of the first part. So we demonstrated the quasi-monochromatic XUV source from gallium without using any monochromator installed in the beamline, in the laser. And in this way, we can avoid the typical loss of about 70% of the XUV flux because of the presence of the monochromator, and the high conversion efficiency of the order of 10⁻⁻⁴ gives us a very promising result that we can use these kind of sources to develop intense multi-microjoule level XUV pulse energies in the laboratory. And in the previous studies, people have used multi-jet configurations for the gases to enhance the generated XUV pulse energies. But here we don't use any multi-jet configurations, but still our method is still open to use those multi-jet configurations to further enhance the XUV pulse energies. And then because the mechanism is new, so this provides exploring the new physics of the resonant harmonic generation that was previously not explored, especially, for example, in the multiphoton ionization regime. And now in the second part of my presentation, I'll talk about our recent experiments where we demonstrated a new kind of resonance that was observed just below the ionization threshold of different ionic species participating in the harmonic generation process. So when we looked at the harmonic spectrum generated from argon gas in different studies, we observed that just below the ionization threshold, studies have shown that there is some kind of resonant enhancement of the harmonic order. For example, especially here we can see that there is an enhancement of the harmonic, which is just below the ionization threshold. And even in this different study, we can see some kind of structure. So we decided to find a similar kind of enhancements in our case. That means in laser-ablated plumes. So previously, because we worked a lot with indium, however, the ionization threshold of indium was at 18.87 electron volts, which matches with the 12th harmonic at the 800 nanometer. And because in typical harmonic spectrum with a single laser beam, we only generate odd order harmonics. So this harmonic order was always missing. So this is why we did not observe this resonance here. And then to observe the resonance here, we decided to use the two-color setup where we overlap the 800 nanometer field with the 400 nanometer field. And in this way, we can generate the full harmonic spectrum containing both odd and even harmonics. And indeed, we see a harmonic enhancement that corresponds to an energy just below the ionization threshold of the indium ions. This confirms what was previously observed in the gases. And we further explored this enhancement using the longer mid-infrared laser wavelengths. And again, the ionization threshold is about 27 photon resonant with the 17-18 nanometers. And again, we see this harmonic enhancement located just below the ionization threshold. And when we change the driving laser wavelength away from the resonance, the enhancement again diminishes. We further changed the driving laser wavelength. So instead of going to the mid-infrared, we went to the near-infrared laser wavelength. So here is the example for the indium. So this is the well-known resonance from the auto-ionizing resonance. This is well-known. However, when we keep tuning the laser wavelength, then we see that there is a new kind of resonance which is observed at just below the ionization threshold of the indium ion, which corresponds to 13th harmonic order at 860 nanometer laser wavelength. Here's the similar spectra. Here are the similar spectra. So again, when we switch the driving laser wavelength, the intensity of the resonant harmonic diminishes. Now the next question was that, does this kind of enhancement for the harmonic order located just below the ionization threshold is universal? Is it a universal phenomena? And then to confirm this, we used tin and chromium. So tin has an ionization threshold at about 14.6 electron volts, tin singly charged ion. And for chromium, it's about 16.5 electron volt. And to our surprise, we did not see any kind of harmonic enhancement near the ionization threshold for both tin and chromium. And then we used gallium target, and to our surprise, we do see the harmonic enhancement just below the ionization threshold of gallium ion. So in some targets, we do observe the enhancement. In other targets, we do not observe the enhancement. And here is a summary. So in tin and chromium, we do observe the enhancement just below the IP, and in indium and gallium, we do not observe. And then when we carefully looked at the IP and the autoionizing state of these species, then we observe that in tin and both tin and chromium, both autoionizing state and the IP, they are located very far away. The distance is about 11.6 eV in case of tin. And in case of chromium, the difference is about 28 electron volts. However, in both indium and gallium, the difference was only 1 electron volts. So this was the interesting point that we looked into, that the distance between IP and autoionizing state is less, and then we see the harmonic enhancement. So in an effort to explain the generation mechanism, the mechanism is still not clear, but this is what we think it could be the possible explanation. So here is the energy level diagram for the indium ion. So we have the ground state at 0 eV. This is the reference. We have the autoionizing state at this autoionizing state at 19.92 electron volts, and ionization threshold at about in case of indium, it's about 18.87 electron volts. So at 1780 nanometer driving laser wavelength, which is the case here, the first figure, we have the multiphoton resonance with the IP. And because these are the broadband pulses with the typical FWHM bandwidth of about 40 nanometers, I would say, or more, we have simultaneously a multiphoton resonance with the autoionizing state. So because of the multiphoton ionization with the IP, these Rydberg states get populated because of the multiphoton resonance. And because the autoionizing state and IP, they are located very close. So the dressed state, which is the 2-photon resonant below, in this case, the 2-photon below dressed state for the autoionizing state, it has an opportunity to get overlapped with the Rydberg cloud located just below the ionization threshold. And because the overlap is possible, so this gives an opportunity to the population in the electron population in the Rydberg states to go to the dress state, and then this dress state can provide an efficient pathway for all the population to get transferred to the ground state. And this could result into the enhancement of the harmonic order located just below the ionization threshold. And similarly, for 860 nanometer laser wavelength, we have another autoionizing state, and then we have another dress state, which has an opportunity to overlap with the Rydberg cloud. And then again, this provides an efficient pathway for the population in the Rydberg cloud to undergo one photon transition back to the ground state. An interesting thing that I would like to mention here is that at 860 nanometer, the autoionizing state that is at 20.04 electron volt, this has the same parity as the ground state. So ground state is of even parity, and the autoionizing state is also of even parity. So at this laser condition, this autoionizing state cannot directly participate in the harmonic generation process because the transition from the even parity autoionizing state to the even parity ground state is forbidden. However, because in this case, the dressed state has an opportunity to overlap with the Rydberg states. So that means that this even parity autoionizing state or a dark state, because it doesn't participate, it doesn't have the ability to undergo one photon transition back to the ground state. This state can indirectly participate in the harmonic generation process through the involvement of the dressed autoionizing state. In this way, if this mechanism is true, then this provides a tool to study these kind of dark states through the harmonic generation, through the high order harmonic spectroscopy. And similarly, similar conditions can be satisfied in case of gallium. So we have a dark state, we have a dressed autoionizing state, which is overlapping with the Rydberg cloud. And again, there is the possibility of one photon transition back to the ground state to emit an intense harmonic order just below the ionization threshold. So this is the mechanism we propose, but there could be many aspects that we still need to think about, but this is what we think could be the possibility. And with our collaborators, we requested them to do some initial time-dependent Schrödinger wave equation calculations. So they can reproduce these autoionizing states and ionization threshold by tuning the parameter of the Coulomb potential that they take into consideration in the calculations. And in case of indium, at appropriate laser wavelength, we do see the enhancement of the harmonic order located just below the ionization threshold. So now I'll conclude the second part, the final part. So we observed a new kind of resonance located just below the ionization threshold, which was made possible by the overlap of dressed autoionizing state with the Rydberg states. And this provides a new kind of resonance, which can provide intense XUV pulses. And because the mechanism of the generation process is new, we are still not having a clear picture. So this provides an opportunity to further do future investigations to understand clearly the underlying process for the corresponding harmonic generation process. So this is the summary. So this was a two-part presentation. In the first part, I discussed with you the harmonic generation process in the multiphoton ionization regime, which resulted into the increase in the enhancement ratio of the harmonic order. And in the second part, I discussed with you the new kind of resonance that we observe just below the ionization threshold with the new kind of mechanism. So I would like to thank our collaborators. So special thanks to Professor François Légaré at INRS, Professor Wesley Skalkov, and Dr. Muhammad Ashik Farid. And also a special thanks goes to the ALS technician team, Antoine Laramé and Philippe Lazon. And of course, thanks to my research supervisor, Professor Sunil Kiyosaki at INRS. Thank you very much. If you have any questions, I would try to answer.
Thanks, Mangaljit, for this presentation. Any question from the audience? Yeah, François Vidal.
Yes, hello. Thank you for your talk.
Thank you.
15 years ago, with Tsunuki, we tried to explain the resonant harmonics, for example, in indium, with different explanation. We tried something different, and it was based on phase matching. So we calculated, since you generate those harmonics in plasma, you have electrons, you have ions, which are generated by the laser. And then, so we used the electron density that we calculated with a code. We calculate the electron density, the ion density, and using Selmayr formula, we could calculate the index of refraction due to the ions and so on. So we explain this enhancement of some specific harmonics by phase matching arguments. So do you still think that this approach is well, if it's a good explanation or if it's a part of the explanation?
Yes, I have looked into your paper. I don't remember all the text, but I remember that you had tried to include the reduction in the absorption of the XUV that resulted because of the presence of a strong absorption, if I remember correctly. Yes, I remember we didn't look into it in detail, but because in our experiments, when we change the driving laser wavelength, we do have a change in the driving in the resonant harmonic intensity. And if I can remember correctly, in your paper, the position of the resonant harmonic was slightly off the location of the strong absorptions.
Exactly.
So
Actually, we need the real part of delta K to vanish, and this always happens a little bit to the left in terms of wavelength, to the left of the actual position of the resonance.
Right. So this is still an open discussion. If you would like, you can please look into it, but we still know very little. So the paper came recently, so we might think of performing additional experiments. We have to think about it, but this is the mechanism we propose. Our collaborators just did the TDSE calculations, which do not provide the real electron pathways in the mechanism.
Okay.
So maybe more complicated evaluations, which can maybe evaluate, which can consider the electron correlations, maybe some new things might come up, but these are the new observations. So we still don't know many things, but we try our best.
Okay, thank you.
Thank you.
Said Kamal.
Yes, hi. Thank you for your talk. I have two simple questions related to the laser ablation of the target. The first one is, I assume that the target is in a translation or rotation stage because it would be damaged at the laser spot. Am I correct?
Yes, you can have the target at the translation and rotation stage, but for these kind of studies, because we were more interested in looking at the shape of the harmonic spectrum. So usually we reduce the repetition rate to, let's say, 10 or 50 hertz.
I see.
So we don't use kilohertz or multi-kilohertz level laser pulse repetition rates. So in these experiments, I tried to make my life easier. So the target was stationary, but we can manually move it. It was not motorized. Yeah, but
and my second question is, with the laser ablation, basically a plume is the vapor of the material, right? That's been ejected. And I was curious if in the case of some of the targets, such as indium, which has a very low melting point, there may be other ways also to generate the vapor, such as simple thermal, heating or electron beam, for example, in vacuum. Would those other techniques that can generate the vapor would be to some degree play the same role or be equivalent to laser pulse ablation?
Yes, so in case of indium, because as you rightly mentioned, it has a very low melting point, which is so with indium, we have seen that it's difficult to work with because it melts easily. So for example, if we work with tin, which can provide us, let's say at 50 hertz, we can have a stable spectrum for about 2 minutes, 3 minutes. With indium, it would go up to 1 minute. So yes, indium is a very soft metal and it melts easily. So yes, that is an issue. But we can always, in future, we can always have elements, indium mixed with something else to increase the melting point and try to see if we have the similar kind of harmonic generation. So there could be other species in the plume, but indium might be dominating. Gallium, indium, arsenic, maybe.
Okay, thank you.
Thank you.
Any other questions? Mangaljit, I have one question for you.
Yes,
So you have about a conversion efficiency of 10 to the -4, correct? Joule level lasers are becoming more and more available. On the point of view of technical requirements and integration, do you see your approach, if your approach could be integrated to a 1 joule laser system to get, let's say, in the range of 100 microjoule of harmonics?
yes, there is a possibility, but an important aspect is like we have to check if for example, if we increase the pulse energy, if there is a saturation, there could be a saturation because, for example, for singly charged ions, if we shoot a very intense pulse, it can, before even going to the peak, it can completely ionize the system. So either we have very short pulse durations so that the system has a time to feel the peak intensity. So we have to check it, but yes, in principle, it's possible.
But let's say, maybe I should reformulate my question. Could we just use a much longer focal length and get
Yes.
a much longer rally length?
Yes, 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 that's possible. The loose focusing geometry, yes, we can always try that. Yes, we can think of these experiments, and we can yeah, sure, we can do.
I recommend we should think about this kind of
Yes,
thing.
yes.
Any other question? Well, if not, let's thank both speakers.
Thank you.
Unfortunately, I will not be able to join on Gatortown because I have administrative responsibilities. So I wish you a good afternoon, and I let now the voice to Heido.
Yes, thank you, Francois. Thanks, Mangaljit and
Thank you.
Louise, for the nice presentations and discussions. And yeah, if you like to continue discussing in a more open format, I put the link to the GatherTown platform down here. We are not that many people today, but still it can be nice to discuss in smaller rounds there. So if you like, you're very welcome to meet there. And I will keep the Zoom link open for a while until I see everybody is transitioned.